Okay. So when we started trying to look at solutions to equations, we were able to draw pictures even if we couldn't solve. And in slopes, we were able to tap along and it would draw curves for us, but we could draw them by following the arrows. And then we started looking at analytic methods for solving those equations. And we did a whole bunch of integration in a whole bunch of different ways. And sometimes, as we saw with problems that left us with solutions that were still defined in integrals, it didn't work. So if I go back to the picture and I say, draw me a button, tell me what the right answer is, draw me the curve without solving it, what is the calculator doing? Well, really, it isn't drawing a curve. It's drawing a bunch of individual dots and playing connect the dots, but it decides how close those dots are going to be arbitrarily. It's not guessing, but it's approximating in a way we did for approximations back in Calc 1. So put on your Wayback Machine uniform and let's dive back into our memories and see if we can remember linear approximation. By the way, this is like the end of chapter 3 in Calc 1, so it was a long time ago. But this also parallels the ideas we did in sequences and series in Taylor's series, so we kind of did it there too. So maybe if that's a little more recent, think about Taylor's series for a minute. Okay, I am breaking all of your calculators and your technology for the next 30 seconds. What's square root of 37? No calculators, no technology allowed. What's square root of 37?
6.
Something, right? Why 6 point something, Jalen? Exactly. And this is just a little bit bigger than 6. So since it's a nice continuous function, it should behave nicely around. So how could I estimate this? I could think about exactly that graph and say to myself, hey, when you're out here at 36, and you really want to know about what's going on at 37, you could draw a straight line. You'd be a little bit over. Why would you be a little bit over? If you drew a straight line at 36, what kind of a line would it be? There's a Calc 1 answer here. A tangent line. And if I look really closely right there, it's very hard to see in my crap. That just says tangent line. It's really hard to see in my very crappy picture. But if you zoom in right there, you would see something that looked like that, right? My tangent line would be above my curve. The square root would be going away. So if I move over from 36 to 37, I'll be off by a little bit, right? But I could use this value off of the straight line, and that would be really close to the square root of 36. What's the equation for the tangent line? Just in general, not this one. How do I find the equation for the tangent line? I need the derivative for the slope, right? So f prime of a, wait a minute. That's going to give me the slope of the tangent line. And then I have a point, right? A, f of a. Yes? I have a slope and a point. How do I get the equation of a line from a slope and a point? I know algebra was a long time ago. Point slope form is what?
Y, or, yeah, y minus f equals m.
And if I move this over, I have y is f of a plus f prime of a times x minus a. I know the y value where I'm starting. Galen, that's the 6 you gave me, right? I can figure out the slope, and then 37 minus 36 goes right in here. So I just need to know what the slope is at that point, and I can use the straight line approximation. If I do the square root of x, then f prime of x is 1 over 2 root x. And that means that at 636, f prime of a is 1 over 12. And that means that the square root of 37 is roughly 6 plus 1/12 of 37 minus 36, 6 plus 1/12, or in decimal, 6.08333 repeating. Because that's the decimal for a 12th. Grab your calculators. What's the square root of 37? Not that bad, right? I'm at least good to 2 decimal places, right? If I round that answer, it's 6.083. 3 decimal places. I'm good to within one, but a 10,000th. Not bad for a half-ass move. All we have to pick is how far over we're going to move. And I can do the same idea with a differential equation. Let's consider this differential equation. Zero 0.1 square root y plus 0.4 x squared. And I want to start at the point 2, 4. Those are my initial conditions. Now, maybe I don't need the entire graph that goes through 2, 4. But what I could do, if I really wanted to, is I could take the graph of this differential equation, my slope field, and I could look at it. Isn't it pretty? This is in slopes. And then I can go, hey, the 0.24, 24, that's there. You'll notice there's nothing below down here because I got that square root of y. Y is only defined when it's only the square root of y is only defined when y is positive. So if I start at this spot right here, oh, that was pretty close. Let's change that to be 2 and that to be 4. How did it draw that picture? That's the correct curve. How the hell does it know? It didn't solve the equation. It did not. In the back of the calculator, in the back of go off to Wolfram Alpha, solve this and start plotting that. It didn't. It followed the tangent lines. How far? That's up to us. What if instead of looking at this whole graph, I just needed to know what was going on at 2.5? I know what the value is when I'm at 2. This right here tells me that y of 2 is 4. I would like to know what is y of 2.5. Without solving this, without this thing in front of me. How do I do this without the technology? Well, I draw a tangent line. Let's decide how many steps we're going to take to get from 2 to 2.5. I'm gonna pick let's do it in one step. I'm just gonna go one step. Well, what is the slope at the point P? According to my differential equation, I can take these values for x and y, put them in here, and get the slope. Y prime of 2, 4 is 0.1 square root of 4 plus 0.4 2 squared. What do you get? People, you need your calculators, your phones, your technology, or you need to do arithmetic in your head. Tell me what this number is. $1.8. And that means if I use Mia's point slope form, the tangent line is y minus 4 equals 1.8 x minus 2. Or move the 4 to the other side. Now plug in 2.5. $4.9. According to my tangent line, if I do the same thing we just did with the square root idea, I can say, oh, we should be at 4.9. Follow the straight line instead of guessing what the solution should look like. I don't hate that answer. That's pretty good. Maybe. But is it really a straight line? starting here and moving over. It's really a straight line there. Those arrows are not all straight, they're not all pointing the same direction. Jumping from 2 to 2.5, that's a big jump. And there's some swirling and curving going around here that I'm not taking into account. Just like when I was doing the square root, I wasn't taking the curve into account here either. So what's another way I can do this and account for that change as we move from point to point? I could use a different approximation than a straight line. But if I wanted to use a different approximation, I would need one of two things. I would either need a power series, because then I would have x's and x squareds and x cubes, or whatever. I need some sort of thing to do that with. I don't want to do that right now. Power series suck. Or I could do this same calculation, but take more steps and follow the curve at each different step along the way. If, instead of moving over by 0.5, I first moved over by 0.1, I'd have a new point, x and y, right? X would be a 2.1. But then I could figure out, hey, now I'm at this spot. Which way should I go? And I'd get a new slope. And I could move over another 0.1. And then I could say, well, now I'm at 2.2. I'm at a new point. Get a new slope. I could iterate this procedure with a smaller step. Now, I could actually take as many steps as I want. I just have to tell you how big each step is. So I'm going to define the step size, call it h. So I would get, from the point I'm starting at, I would get a slope. I would move over that far. So I start at some point, x0, y0. And then I say, okay, find y prime at x0, y0. Just like we did, we came up with that 1.8, right? And then plug in a new x value, one step over. I get a new point. I get a new y value. I now have x1 and y1. And then I can do this again and again and again and again. Now we'd have to do this how many times? If I'm moving by 0.1, I have to do it 5 times, right? If I move by 0.01, I'd have to do it 50 times. If I move by 0.001, 5,000 times. I can write computer code to do this. I'm not going to do this by hand. I'll do the small one by hand just to show you what the hell's going on. Our differential equation is y prime equals 0.1 square root of y plus 0.4 times x squared. That is our function f of xy. That's our slope, right? In our linear equation, we would plug in two, 4. That's our starting point, right? 0.0. So this is x0 and y0. So far, so good. Y prime of 2, 4, we already worked out, was 1.8. Now, our linear approximation. What was our linear approximation again? We wrote the equation down earlier.
F of A
Plus,
plus F prime of A times X minus A.
well, wait a minute. The new x value is just h units bigger, right? So this is going to be 2.1 minus 2. I moved over by 0.1. Isn't that just 0.1 in there? That's my step size. As a matter of fact, this is always my step size. So I now know y1 is really 4 plus 1.8 times 0.1, which is 4.18. I have a new point. My new point, P1, is 2.1, 4.18. I do it again, which means I need y prime of 2.1, 4.18. Or, since we called that f of xy, that's f of x1, y1. Isn't it? And that's going to go and be my new slope. I need a number. Lots of decimals on this one, right? What's your slope this time? This number is gross. Square root of y times 0.1 plus 0.4 times x squared. Billions of decimal places, right? $1.968450483. I'm being pedantic and writing them all down. So now y2 is where I started, 4.18, plus slope times what? My step size, 0.1. So I'm going to take the slope we got, multiply by 0.1, add that to 4.18. Notice my slope is bigger than 1/8. So this went up, it went up a little bit more than it did last time, right? If we just used the first straight line of 1.8, it would have only gone up a little, but now I went up further because I went to 1.97, went to a bigger slope. So I didn't go over into one straight line, I went tick and then ticked up a little further. I made a little two pieces of straight lines, but the second one is steeper than the first one. And I can keep going and going and going and keeping track of all of my decimal places. And isn't this just so much fun? I got to do this 3 more times because I need to get to Y5. It's going to take me 5 steps. I got to get to Y5. Questions? This is Leonhard Euler's method for constructing a sequence that takes you to the right answer. The next step, Y value, is found by taking the last Y value, finding the slope and multiplying by the step size and adding them together. That's it. Over and over and over. But I did say earlier that this was a pain in the ass. I'm a nice guy. In our reference file section, you'll find 3 Euler files. The first one is a .8xp file. That is a program for an 8.3 or 8.4 calculator. See the USB port on the top of the calculator? The same one that's on the side that you can charge your calculator with if you have the newer version. If you can connect this to your computer, you can just download that program right on here. At which point, what you see in the calculator is what is written on that second sheet. That second file says Euler method TI program. That's a PDF file. Those are the instructions. I literally just printed the program off my calculator. If you don't have the cable, you can type the program in using the commands on the calculator. You'll have to read the chapter, I believe it's chapter 15, on how to type the program commands in, but that's available on our Canvas page and on the manual for the graphing calculator. The last one is an Excel sheet with an example done there instead. But I promise I didn't eat it. Where did it go? There it is. We'll get back to that. If I go to the programs, having loaded this program into my calculator, I have a whole bunch of programs in here. I just called it Euler. There's my program Euler. And the first thing it says when I go to run it is, hey, make sure you have the function in. If you don't, we got to go back and put the function in. It says a function of t and y, so there are no x's in this thing. Program doesn't run in x and y, it runs in t and y. So I'm going to quit this and I'm going to go to edit the function. Under program, go down to Euler and hit this thing that says edit. Display, enter a function of t and y, press enter when done. I go down and here, this line right here with the arrow K, that, the left side of the arrow, is the function I want. So, what was our function? One we were just using?
.1 squared y. Plus 0.4 x squared.
0.4. It's not x this time though. It's t squared. And then I need to delete all the rest of the stuff until the arrow. Now the function's in the right place. Right? So I quit out of editing. Let's run it again. I know the function is in the right place, so I can just hit enter. What was my starting x value? 2. My starting y value? 4. How many steps was I going to do? And each one was going to be 0.1. There's your first step. There's your second step. Look familiar? Same number we came up with. Step 3, step 4, step 5, all done. All I have to do is hit enter over and over and over. Doing this by hand is an exercise in tedium, boredom, and decimal errors. I cannot tell you the number of times I've copied a decimal down wrong, fucked up the whole thing. I don't have to. I don't even have to do it in the calculator if I don't want to. As I said earlier, here's one in Excel. Now, this is actually the example in the textbook, so the function is different. The function is 2x plus 3y plus 1. So over here, you'll notice in this box where it says y prime of sub n, that's calculating the slope, and the slope is 2 times the thing in the x box plus 3 times the thing in the y box plus 1, which is exactly the function we want. So this function up here is doing this for every one of these boxes using these numbers over here. And it's increasing the x values based on my step size, which is written up there in box B2. You want to change the step size? You're going to need more rows. Just copy down more rows. And all you have to do is put in the starting point in row 0. Wait, keep going. The one we were doing make another copy of this and I can edit it. Move to the end, make a copy, bang. Our function was 0.1 times the square root of y plus 0.4 x squared, right? And we were starting at 2, 4. See how all the numbers started to change? But I need to change this formula, otherwise that's the wrong y prime. So our formula is 0.1 times the square root of y. Wrong button. Got to tell it what cell that is. Oh, There's a reason it didn't let me move over. I forgot to put the equal sign at the beginning here. Equals. There we go. See how it lit up the cell I was using? Forgot to hit equals. Plus 0.4 times this one to the second. And now 4.18, 4.376. Aren't those the same numbers we got? And if I want to keep going, insert some blank rows here. I can grab and copy this down 3 more times. Ta-da! I'm done. And for the record, 5.076757934. The final value off my calculator. The same one that's sitting right there in row 5. You want a smaller step size? It's going to take more steps. 0.05. Oh, I only want to go to step 10. There we go. Hey, wait a minute. That answer is different, isn't it? Is that one bigger or smaller than the last one? But just a little, right? Why? Because that curve kept going up, right? So the tangent line would always be a little bit below. And the actual value would be a little bit higher. So if I take smaller steps, I get to make a little more curvy of a path. And that allows me to be a benefit. Excuse me. Now I can actually ask how far off it is. This problem is going to suck because I don't know how to solve this differential equation. But in this one, that's y prime, right? Let me close this for a second. In the example we were just looking at, y prime equals 2x minus 3y plus 1. Notice I can rewrite that. Y prime plus 3y equals 2x plus 1. And when I've rewritten it, Mia, something wonderful happens. What something wonderful happened here? I'm putting you on the spot, I know. That turned into something I know what to do with, because that one's linear. Y prime plus p times y equals some function of x. That's a form I recognize. I know how to do this one. Which means I could actually solve it. And then at each and every step of the way, I could tell you how far off my tangent line was, because I would know the actual solution. Now, in order to do this, I need my initial condition, which I forgot to write down, 1, 5. That's my starting point. So I need mu, which is e to the integral of 3 dx, which is just e to the 3x, which means I'm going to have to do integration by parts, and then I'm going to have to solve for my initial condition. And oh, joy. I know how to do this. I am going to make the amazing claim that you do too. You could separate that and do the 2x e to the x part separately from the 1 e to the x. That way you still have to do integration by parts, or you can leave it combined and do integration by parts in one fell swoop if you want. It's up to you. But once you do that, you do the initial condition, you plug that in, you can actually get the appropriate y equals 2/3 x plus 1/9 plus c e to the minus 3x. Solving for c, you get 38e cubed over 9. Why do we get such a sucky looking c? Because my initial condition had p at an x value of 1, not an x value of 0. If the x value was 0, I'd get a much nicer looking solution, but I didn't. Which means I can actually write out the equation. I can plug into the equation and subtract the approximation from the value. The absolute error Okay, lab people, what's absolute error? Anybody taking a lab this semester should have dealt with this at least once already this term. Yep, you did it in physics, you did it in chemistry, you did it in every lab you did actual measurements in.
Total amount of error.
That's sum of error, but I'm looking, what's the definition of absolute error? Well, what's absolute? Absolute's absolute value. So this is the absolute value of the actual value minus the approximation. And we get the actual value by using this. The function we just came up with right here would give us the actual value for each x value we were computing. We did the approximations, that's what's sitting in our Excel sheet, right? And then I can do relative error, which is absolute error divided by the actual value. Notice the absolute value bars on the bottom there. That way I don't have to worry about negative relative error or positive relative error. Absolute error is already an absolute value. We take the absolute value of the bottom to be consistent. By the way, in our Excel sheet, those are the y values we were just looking at, right? For this problem. Notice it says here, errors. Here's where we worked out the solution. Here's where we did the actual value by plugging into this, and we subtracted, and we got the relative error and the absolute error in both cases. Modern computing systems do this for us. I like Euler's method because it is simple. And I say that a little jaded here. It's simple because it's straight lines. It's not simple because it's easy to do. It's simple because it's simple to understand what it's doing. It's saying, I go in a straight line to here. Now which way am I supposed to go? Go in a straight line to the next spot. Now which way am I supposed to go? Go in a straight line to that spot. Over and over and over. And that's all slopes was doing when it created this picture here. It was stepping over and moving up and stepping over and moving up and stepping over and moving up. Its steps are just tiny. Because it's a computer, it can do all those steps very quickly. As a matter of fact, there is a numerical methods application in slopes. And notice it says right there, Euler. Type in the equation, give it the starting value, chug, 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 it's done. But there are also two other methods here, RK2 and RK4. Two other numerical methods by the name of Runge Kutta. Rungekutta, two people. Were developed whether you use degree 2 or degree 4, depends on the situation you're working with. And by the way, all of these have the error calculation built in. And you can see there's even an all button, so it will do all of them together and allow you to compare them. If you're interested in understanding what's going on in Runge Kutta methods and others, you should take numerical methods next semester. That's what we're going to talk about. There are dozens of other numerical approximation methods. Euler is just the most straightforward in the way it works. Questions? Yes.
Calculator program,
Yes.
is that the same one as like previous calculator?
Yeah, if you used this in Calc 2 or yeah, because we did this in Calc 2. If you downloaded that in Calc 2, it's the same program. You're welcome. Yay! Well, you can always check against the PDF file, make sure you haven't deleted a line or anything like that. Good idea. The program that allows you to go back and forth between your computer and your calculator is from Texas Instruments directly. See this little blue and green two-headed arrow down here on my screen? That's the TI Connect software. That's free on the TI webpage. So you can get that, and all you need is the cable, which is, fortunately for us, a standard mini USB cable. That end. And then you can just plug, if your calculator uses a particular charging cable, you plug that directly into your computer, go for it. But mine's the old one that has the batteries in it still, so it doesn't have a charging cable on it. Do I expect you to be able to do this by hand? Well, yeah, it's not hard. It's just going to take forever. So if I'm going to make you do something like this, we're going to do a really small number of steps. Really, I'm going to rig the hell out of it so it's easy numbers to deal with. But the process is direct. Questions? So when we're solving differential equations, we really have three things. Draw me a picture, find me numbers without solving, and then let's try and do the calculus and actually solve this sucker. Why? Spent a lot of time learning these methods to start with. I want to put them to use. Please note a slight change in our schedule. Question and answer day is tomorrow. Which makes the homework due Wednesday, not Friday. Because I'm going to do these two sections, and that's more than enough for an exam. Hey, we're a third of the way into the semester, a quarter of the way in the semester, we should have an exam now. Breathe deep, people. We're getting there. I will see you all tomorrow. Have a wonderful rest of your day. There you go. I put it back up, I promise.